Hey pre-cal. So in this video, we are going to be talking about log applications. You've done some or a decent amount of review with exponential and log equations, right? So simplifying, solving, like using the properties. You did graphing and you did exponential applications. So this one we're going to focus in on log applications, which is a little, I guess it's new to us. It's a little different. So there are some resources that I'm going to encourage you to, if you have a printer, to print out. If not, maybe have it pulled up or like your screen split, or that you're writing things down on a separate sheet of paper. There is a reading, which I'm going to highlight throughout this video. And there's also a worksheet, which is technically the homework worksheet. And I'm going to be going through, I believe there's 7 questions on that worksheet, and I believe I'm going to do 4 of them. I think that's what I'm doing. So with that being said, let's get ourselves started. So there's a few different applications that we're going to focus on. One of them is related to earthquakes and the Richter scale. So as you may know, the intensity of an earthquake is measured by the size of the seismic wave that's generated by that earthquake. So let's see, is my pen working? Oh, it is. Okay. So the value S sub 0, which you see in the formula, and I will go through that in this as well, was set in 1935. And it is approximately the size of the smallest seismic wave that can be measured at the time, right? So the units actually don't matter because of this ratio, right? It changes proportionally. So an increase of the earthquake's intensity by a factor of 10 corresponds to an increase in 1 Richter value or 1 Richter magnitude. Okay, so that's one application, is earthquakes and the Richter scale. So pretty interesting if you take a look at these. So these numbers vary across such a huge scale that earthquakes are usually reported using the Richter magnitude scale, which is a logarithmic scale using the common base of 10. Very interesting. We also have sound intensity and decibels. So the intensity of a sound is the amount of energy carried by the sound throughout each unit of area. The human ear can perceive sound over an enormous range of intensities. The ratio of the intensity of the quietest sound that we hear, the intensity of the loudest level that causes pain, is over 1 trillion. How crazy is that? So this is also a logarithmic relation, which is a logarithmic scale using the common logs as well. So for this, the value E sub 0 is 10 to the power of negative 12 watts per square meter. The intensity of sound is usually measured in watts per square unit, but the units don't matter once again because we're looking at the ratio. Multiplying sound intensity by a factor of 10 corresponds to adding 10 to the decibel measurement. Okay, and we'll sum this up with the equations, which I know were in that reading as well if you took a look at it. I just wanted to provide a little bit of background information as well. And then the last thing I'll be talking about is star brightness, or it's called apparent magnitude, and it's more accurate than just magnitude. So the ancient Greeks divided the visible stars into 6 groups based upon their brightness. The next brightest star was called the second magnitude star, right? So the typical first magnitude star were about 100 times brighter than the typical 6th magnitude star because there are about 5 steps in going from the first to the 6th. This means that each magnitude, the brightness should decrease by a factor. So apparent magnitude, I said that, right, is more accurate than just magnitude because we're measuring how bright the star appears from Earth. It is, again, this ratio, right? So although the value of B sub 0 was originally set, oh wait, sorry, wrong line. The unit used to measure brightness does not matter because any change in the scale of units appears in this ratio, right? So this, the actual magnitude is that. So these are the 3 that we're going to be working with throughout this video in this lesson. So in our log applications, we had earthquake, decibel scale, and apparent magnitude. And we have these 3 formulas, which these are not on your quiz that we will do when we see you next. This is a new objective. This is our last objective. So reference these formulas as we work with this. So what do these actually mean? S sub 0, E sub 0, and B sub 0. S sub 0 is the smallest measurable seismic wave. S is the actual seismic wave. E sub 0 is the quietest sound a human can hear. E is the actual sound. And finally, for apparent magnitude, we have 5/2 log B sub 0. Look at that. B sub 0 is the brightness of an object with 0 magnitude. And B is the actual brightness. So we are going to be using these formulas throughout these applications that we're going to work through. So I'm going to start with actually number 4 on the handout. So if you join me with number 4, I'm going to go a little bit out of order here. So this one, suppose that your cell phone rings with a noise of 74 decibels, and you normally speak, so ringing 74 decibels, you normally speak at 61 decibels. What is the ratio, there's that word again, of the sound intensity of your cell phone ring to the sound intensity of your normal speech, right? So we're really working with two things here. We have the decibels for the phone ringing, and we have it for you speaking. It's two different things, and we want to know the ratio of phone ringing to speech. So let's see. We can actually set up, here, you know what, I'm going to write this. We actually probably want to know what the formula we're using is, right? So let's take a look. I'm going to write it at the top. Right? And really, I have two of these. And E is the actual sound. This is the decibels. So this 74 equals to this. 61 equals to this. Right? So I should be setting up two equations right now. 74 equals to 10 log E sub ring over E sub 0. 61 equals 10 log E sub speech over E sub 0. My goal is to figure out what is E sub ring over E sub speech. Right? Like that's what it's saying. The intensity of ring to the intensity of speech. So what can I do with these? Oh, I can subtract them. And what happens when I do that? I get something that looks like this, right? I get 13 equals 10 log E sub ring over E sub 0 minus 10 log E sub speech over E sub 0. Well, when you're subtracting, what does that mean that you do with the arguments? Divide. Right? So now I've got 13 equals 10 log E sub ring over E sub speech. My goal is to isolate that, right? That's what I want to solve for. So I'm going to go ahead and divide by 10, and this is what I have. Then we have to think back to our properties, right? And oh, isn't this the common base? It's 10. So we get that it's 10 to the power of 1.3 is going to equal to that ratio, which is about 20. Right? So the ratio is about 20. The sound intensity of the ring to the sound intensity of your speech. Right? The ring is more intense. So let's see. Part B is telling us, and I'm going to write out what we actually just had on that problem. We got 10 to the power of 1.3, which was about 20. So this is asking me, suppose your cell phone rings with a noise. Oh, wait, sorry, I don't know why I'm reading that again. Given that the human ear perceives each increase in 10 decibels to be doubling of loudness, how many times louder does your cell phone ring than your speech? Right? It's 20 times more intense. 20 times more intense. So what is that going to be? Well, instead of doing 10 to the power of 1.3, each increase in 10 decibels is like doubling. So I should be doing 2 to the power of 1.3, which is about 2.46 times louder. Let's try another one. I'm going to go back. I'm actually going to do number 2. So number 2 is saying the most intense recorded earthquake in Texas occurred in 1931. It had a Richter magnitude of 5.8. If an earthquake were to strike Texas next year that was 3 times more intense than the current record in Texas, what would its Richter magnitude be? Right? So let's see. We're going to end up with something minus 5.8, right? I want it to be 3 times as much. And I'll explain where I'm getting this in a second. Equals, well, what was the equation here? My fault. I didn't write the equation for you guys at the beginning. This is the Richter magnitude is log of S over S sub 0. So I want this ratio to be 3, right? I want to get log of 3 when I do this. Okay, so I want this, when I subtract them, to be equal to the log of 3. Right? When I subtract their magnitudes, it should be equal to the log of 3. Because realistically, I mean, I don't need to do this entire piece, but I should be able to subtract them, and then equals to log of S over S of new over S sub 0 minus log of S sub old record over S sub 0. When you do this and you divide, and I do S sub new over S sub 0, instead of dividing by a fraction, let's multiply by the reciprocal. Oh, those cancel. Right, so this right here, and I've said that I want it to be 3 times as large. So 3 times is more intense, so this should just give me 3. Right, so I really right now have this negative 5.8 equals to log of 3, and I should go ahead and add 5.8 in order to solve for whatever this is. So whatever log 3 plus 5.8 is going to be the Richter. 6.28 on the Richter scale. That would be the magnitude of the new one that is 3 times more intense. Let's do another one. Let's do number 5. I'm skipping around a lot. I'm going to do 5, and then I believe I'm going to do 7. So Sirius, the brightest star that can be seen from Earth, not counting the sun, has an apparent magnitude of negative 1.4. Vega, which was the North Star about 12,000 years ago, slight changes in Earth's orbit lead to changing North Stars every several thousand years, has an apparent magnitude of 0.03. How many times brighter than Vega is Sirius? So I'm talking about apparent magnitude here. So let me write the formula that we're going to be using. 5 halves log of B sub 0 over B. And B is the actual brightness, and B sub 0 is the brightness of the object with 0 magnitude, if you recall what we did a little bit earlier. So let's see. Sirius has an apparent magnitude of negative 1.4. So let's set that up. 5 halves log of B sub 0 over B. What else do we know? Vega has an apparent magnitude of 0.03. Equals 5 halves log of B sub 0 over B. Right, and so this is Sirius, this is Vega. So let's go ahead and subtract them. I'm going to end up with negative 1.4 minus 0.03 equals to 5 halves log. When you divide these, what's going to happen? I'm going to end up with Vega over Sirius, right? The actual brightness of Vega over the actual brightness of Sirius. Well, we want this. It says that's what we want to figure out, right? We want to figure out how many times brighter is Vega than Sirius. So we need to solve for that. So I can go ahead and actually do this subtraction, right? So that will give me negative 0.572 equals log of Vega over Sirius. So 10 to the power of negative 0.572 equals that ratio, which now I can't read my own handwriting, but 0.268, I think is what I've written down, but now I'm not sure. 10 to the power of negative 0.572, 0.268, yep, that's what my handwriting says. 0.268, how many times? Times as bright. So it's less bright, isn't it? Very interesting. Oh wait, did I do it? No, I did it the right way. Yeah, okay. Very interesting. Okay, let's look at one more. Let's look at number 7. So Neptune has an apparent magnitude of about 7.8. What is the apparent magnitude of a star that is 20 times brighter than Neptune? So let's see. 7.8 equals, it's the same formula we just worked with, 5 halves log of b sub 0 over b, right? So if something is 20 times brighter than Neptune, I actually want this to be, well, okay, so I don't know what it is, so let's set it up. So I would use something minus 7.8 equals 5 halves log of, well, this is going to end up being 20, right? Because of how I just set it up. Like I want it to be brighter than this one. So this is going to be the brightness of Neptune, right? So you want it to be, let's say, brightness of other. I want to end up with brightness of other over brightness of Neptune to be 20. No. No, I want it to be 1 over 20. Oh no, sorry, I'm mixing this up. I want it to be minus something. Right? So, or I could say that I wanted this to be 1 over 20, which would have been acceptable too. So let's set this, let me fix that a little bit. So instead of saying something minus 7.8, because this is flipped, my fault guys, 7.8 minus blank has to equal to 5 halves log 20. And then we can go ahead and actually solve this. So if I'm trying to isolate this question mark that I have, I'm going to end up with 7.8 minus 5 halves log 20 equals to whatever it is. When I go ahead and actually do that, I end up with 4.547 is what it is, right? So what is the apparent magnitude? 4.587. Okay. So there are 3 others, I believe, that I went through 4, and there's 7 questions on here. There's 3 others. I did not do number 1 with you all. I did not do number 3, A or B. And I did not do number 6. So those I have left for you guys, and we will spend some time. We can go through this and talk about them and do some of them in class, but hopefully you got these down and you can see what questions you might have that you want to bring to us. So again, like this is not on the quiz that we will have when we see you next. It'll be the things that we did prior to this. So see you all next time. Thanks for watching.